it. Thank you. The slide, full screen. Okay, so what we started out is the discussion on the time-dependent perturbation theory because there was specific needs for it. So in a simple dipole transition of 2p state decaying to 1s, or other decays you're looking at a homework problem right now, just the first order Fermi golden rule was sufficient. But there are other processes like 2s state decaying to 1s by emitting 2 photons, and a scattering process of atom and a photon. You need to go beyond that. So that's why we started to develop the formulas for it. And for that purpose, we introduced this new picture called interaction picture. So unlike Schrodinger picture, where operators don't change as a function of time, or Heisenberg picture, where state doesn't transform as a function of time, in an interaction picture, both state and operators transform as a function of time. And for this purpose, we introduced this new time evolution operator called UI, where you can you can expand this in terms of the power series in a perturbation to the system V. So H naught is a zeroth order Hamiltonian, which you have solved exactly. So you know all the eigenstates and eigenvalues and all that. And V is the perturbation you don't know how to solve. And by using this UI time evolution operator, you can expand this in power series in V, roughly speaking, that because H naught piece cancels in the exponents. So that's what we started to do. And by taking differential of the UI operator and then integrate it again, we came up with the systematic power series expansion of the UI operator, time evolution operator, in the perturbation to the system, VI. So what we need to do is to grab this formula now and work out the amplitude for some transition process. So what we did first is to apply this to the first order in perturbation theory. And we wrote this VI out explicitly because we know the eigenvalue problem of H naught for the energies of I and F. And then did the time integral. But the time integral actually can be done in 2 parts. We took the second power of this time integral, and we took 1 power to be in the limit of the infinite time, reducing into delta function. But the other power of this time integral, now that there's a delta function together with it, we just inserted the argument of delta function, namely that exponent turns into 0, so that this integral just turns into the time interval. So that's how we came up with the Fermi's golden rule, namely that transition probability per unit time is given by this famous Fermi's golden rule. So that's what we did on Wednesday. So we basically verified and rechecked Fermi's golden rule to come up from the first order in perturbation theory. So now we would like to actually go ahead and use the second term in the expansion of UI in second power in the perturbation and work out the transition amplitude coming from this piece of the time evolution operator. So that's what we like to do next. And eventually we applied it to some physical processes like the 2S decay later on. So any questions about where we're heading? Sahil?
Oh,
you want to speak?
Unmute myself.
Oh, okay. Because you were not muted, I thought you might be one actually to speak up. Any other questions here? Okay, so let me just go ahead and look at the second order in perturbation theory. So this is the expression.
Yeah, I think there's 2 of me for some reason.
Oh yeah, I see 2 of you. You have a doppelganger.
Okay. I'll try to figure it out and try to remove the other one.
Okay. Yeah, make sure you don't meet the other one because it will disappear. So this is the transition amplitude from initial state I to final state F using the piece in the expansion of UI, the time evolution operator, to the second power in perturbation V. And definition of this VI operator was given by the operator sandwiched by the time evolution according to the 0th order Hamiltonian. So that was a definition of how operators change the function of time in the interaction picture. So I just stick in that definition over here. And on the leftmost and rightmost time evolution operator with H naught, they just pick up the eigenvalues of energy in the initial state and energy in the final state. So I can take them out from this matrix element. But there is a piece which is in between two perturbation Hamiltonian. So the only way we can actually work this piece out by inserting the complete set of states in terms of the eigenstates of the H naught operator. So by putting this 1 in here, this is the 1 with the sum over all the intermediate states. Then this sum is just 1. So that's the same as what I used to have on the previous line. But now that I have inserted these eigenstates of the H naught, this H naught in the exponent now turns into the eigenvalues of the state M. So I can then take this as a number out of the matrix element. So I have two matrix elements of the perturbation Hamiltonian from initial state I to whatever this state M may be. And another matrix element of M, again, going with the perturbation Hamiltonian to the final state of our interest. And you have to sum over this state M. So this M is called intermediate state, simply because in perturbation theory, I goes to M as an intermediate step, and then M goes to the final state, F. So M is called intermediate state because of that reason. And now that all the time dependencies of this integral turn into these exponential factors, so this is all the integrand I need to think about in terms of time integrals. And all the operators are now contained in this matrix element, as I said, from initial state, intermediate state to the final state. So I'm supposed to carry out this time integral, just like what we did with the Fermi's golden rule at the first order in perturbation theory. And here, I took the time interval to be from initial time ti to final time tf. And I have this double integral with the time ordering. So this t2 integral goes from ti to t1, and t1 then is integrated from ti to tf. That's a triangle of this the two-dimensional plane of the time integrals we talked about on Wednesday. Okay, so the rest is to just carry out this time integral. Any questions about this? Okay, so let's go ahead and do that. And of course, we did do it a little bit on Wednesday, but it went fast. I'd like to go a little bit more slowly this time. So we are interested in the limit of very long period of time to have this transition to be completed. So in effect, we're taking the limit where this initial time goes to negative infinity, so that we are talking about very long period of time. But if you just look at this exponential factor, then they keep oscillating when the ti goes to negative infinity. So this integral is actually, in some sense, ambiguous or non-convergent. So we play a trick to force this integral to become convergent by putting in this extra factor of exponential e to the t2, epsilon t2. So epsilon is a tiny positive number. And when t2 integral, where t2 goes to this lower edge of the integral ti that is sent to negative infinity, then this exponential factor damps exponentially because t2 being negative, epsilon being positive. So this gives you an extra convergence of the integral we would like to carry out here. So this is just a pure mathematical trick as far as we're concerned at this stage. It ends up having actually a meaning later on for physics purposes. We will see it come back and talk about it when it comes to it. But right now, this is meant to be just a pure mathematical trick. So by carrying out a T2 integral of this double time integrals over here, the T2 integral would give you this factor. Just because T2 dependence, it has this exponent of EI minus EM that comes into the denominator. I keep track of the factors of minus I and H bar here. And this is the upper edge, and this is the lower edge of this integral. But now that I stick in this extra epsilon factor in here, so this second term in the numerator damps exponentially so that I can ditch this term from the expression. So that makes things a lot simpler now. Then I have the remaining T1 integral. And T1 integral now comes with EI minus EF, because this intermediate energy piece cancels in the exponent. So here I have minus EM. Here I have plus EM. So they cancel in the exponent. So the integral really just have to do with the initial and final state energies. And that's the expression we already looked at in the Fermi's golden rule at the first order perturbation. So by sending this time interval to infinity, this ends up being the delta function. Of course, we take the absolute square of the amplitude to compute the probability. When you do so, another factor of this time integral is then turned into the time interval, so that we can factor time interval from both sides to compute the rate of transition, just like what we have done with the Fermi's golden rule. So the only new aspect is this matrix element, L amplitude, which goes from initial state by perturbation to an intermediate state. You have a factor which is called the energy denominator, goes like 1 over the energy difference from the initial state and the intermediate state. And there's this obscure I epsilon factor coming in here. And then another transition from the intermediate state due to the interaction, the perturbation Hamiltonian to the final state. So we are talking about this two-step process now. The initial state by perturbation first go to the intermediate state. You have this energy denominator from this intermediate state. And then the intermediate state finally goes to the final state. And that's complete. That is how it completes the transition we wanted from initial state all the way to the final state. So that's the idea of how things go at the second order in perturbation theory. So, this is kind of technical, but I think the idea is clear enough. All we had to do is just to perform this two integral over time in the time evolution operator. We played this little trick to force the convergence of the result, but otherwise, all we had to do is to just perform this double integral over time. And so that's how we ended up with this expression for the amplitude. Okay, any questions about this? No? You guys are kind of quiet today. I don't know what's going on. Are you tired? I can see why you might be tired, because in the middle of the semester after all the midterm. Are the midterms over now?
Yes, for me.
Okay. So I hope you feel more relaxed then. So now that we have this amplitude of the second order perturbation theory, we of course would like to use it. So this is just a summary of what we got. So this is the second order result. So that's a generalization of Fermi's golden rule. So amplitude, we worked out at the first order perturbation, which is what is used for Fermi's golden rule, is this matrix element. Now we have a second order term to this matrix element of initial state going to intermediate state, energy denominator, and the intermediate state finally going to the final state. It may be also useful to just do a sanity check that it works out dimensionally. So this matrix element is a matrix element of the perturbation Hamiltonian. So this has the dimension of energy. And second order piece has two matrix elements, each with dimension of energy. But now I also have the energy denominator. So 1 power of the dimension of energy cancels, and the result also has dimension of single energy. So it's consistent to add them up. And amplitude has this energy of the dimension of energy times the delta function of energy, which has the inverse dimension of energy here. So the amplitude is 8 dimensionless. And the rate of transition, here I use square of this delta function, and 1 power of the delta function turns into energy, the time interval. So you divide both sides by the energy of the time interval to get the rate of transition. I call this gamma. In the lecture note, I use W, and for a reason, and you'll see why later on. So the rate of the transition is then given by this expression. Again, if you ignore the second order piece, then that reproduces the Fermi's golden rule. But now I have this additional piece. at the second order perturbation theory, and we can apply it to physical processes. Okay, so that's a summary of the second order result for the Fermi's golden rule. Any questions about that?
Yes, I have a question that
Go ahead.
is gamma just the absolute value of a squared, right?
No, a squared over time interval. This is the rate of transition.
Yeah. But my question is that you have a like 1 over h bar in the expression of a, and you also have another h bar at the very end of the expression. But then
because there's a h bar in delta function. So you square this, you get 1 over h bar squared. But
yeah.
I have another power of h bar here, so that cancels one of the powers of h bar here. So that's how you end up with 1 over h bar without square.
But what about the other one that you just squared?
The other one turned into time interval.
Okay.
Is that okay? So
yeah,
let me back up. So this is the bottom. So one factor of this time integral gives you delta function.
Okay,
and the other factor gives you this time interval. It's okay?
Yeah, I see. Thank you.
All right, good. Any other questions?
Why does the epsilon T2 make it vanish? Or converge, sorry?
So once we have epsilon here, and I'm sending Ti to negative infinity, right? So epsilon I times minus I is 1, and epsilon is meant to be positive. Ti goes to negative infinity, so that this factor is exponentially damping and it goes to 0.
Okay.
So that's how we force this integral to converge.
I see. So if we didn't have that, then what would be the case, I guess? It usually results in delta function.
Yeah, then this factor keeps oscillating. So I don't know how to take the limit of infinite time interval in that case.
Oh, okay, I see.
All right, any other questions? Okay, so now you seem to accept that this is the result of the transition rate at the second order perturbation theory. We like to use it. So the way we use it, by looking at this Hamiltonian again of the point particle coupled to electromagnetic field, which of course includes now the creation and annihilation operator of the photon. So the idea is that when you look for example, decay of the 2s state into 1s state by emitting 2 photons, then you can use this Hamiltonian at the first order using the last term, which has 2 powers of the vector potential. Because you are supposed to create 2 photons. Initial state is 2s state with no photons. Final state is 1s state with 2 photons. In order to use this first order term, V has to create 2 photons. But this last term can do that indeed, because each factor of vector potential contains creation operator of the photon. I have the second power here. So this last term, I stick it into the first order term to create 2 photons to let 2s state decay into 1s state with 2 photons. On the other hand, when you used first 2 terms of this, the perturbation Hamiltonian, the first 2 terms have only 1 power of the vector potential. So I have to use it twice to get 2 photons in the final state. And that's why we need to use the second order piece. So from initial state, I use these first 2 terms in V, and that will lead to the intermediate state with 1 photon with energy denominator, and intermediate state with 1 photon, again using the first 2 terms of the interaction Hamiltonian, that will create yet another photon, so that you have 2 photons in the final state now decaying to 1s state. So I need both pieces actually to compute the 2s state to 1s state. So that's what we're going to do. Any questions about this? Okay, so this is just an actual name. So when you talk about this state M, I call this intermediate state, but often it comes with this adjective that this is actually a virtual intermediate state. And what's meant by this is that thinking about this energy conservation, initial state and final state have the same energies enforced by the delta function. So there is overall energy conservation going on, which is good. Initial state and final state have the same energies. But when you look at this matrix element, in initial state I goes through this intermediate state M, but this state M doesn't have to have the same energy as the initial state or final state. In particular, if it has the same energy, we seem to have a singularity. So it better not have the same energy, actually. So this intermediate state doesn't seem to conserve energy. How come that's possible? But we know that in quantum mechanics, there's an energy time uncertainty principle. We'll come back and talk about this later on. So intermediate state doesn't have to conserve energy. There is delta E going on. But energy time uncertainty principle tells you that if you borrow energy so that you can make a transition from intermediate initial state to intermediate state, you may have to borrow energy. So energy is not conserved. But as long as you return the borrowed energy within a time interval delta t, which is of the order of h bar over delta E, that's okay. So that's why we say this intermediate state is in some sense virtual. You don't observe this state, because if you want to observe state, then you have to make sure energy is conserved. But it doesn't. So that's why we call this intermediate state to be virtual. So you do go through this intermediate state in the spirit of perturbation theory, but this intermediate state M is not meant to be observed, and hence it is virtual. So this second order perturbation theory tells you that the quantum mechanics is indeed something fuzzy. It's always uncertain. Even energy is uncertain as far as this intermediate state goes. But as long as you don't observe it, that's okay, because initial and final states you do observe satisfy the energy conservation law. So that is already hidden in this formula, that there is this concept of something virtual intermediate state going on in the spirit of perturbation theory. Any questions about that?
Why is it the reason you can't observe the state exactly?
Because if you do observe this state, it has to satisfy energy conservation, right? So initial state and final state is we do observe. You do observe 2s state, that's the initial state you prepared. You do observe 1s state in 2 photons, that is something you do observe, and they satisfy the energy conservation. But this intermediate state M doesn't have the same energy. Therefore, if you observe, that is not the state that can appear. It violates energy conservation. Thank you for asking. Any other questions here?
I also had another quick thing.
Go ahead.
In my 137B, we also covered time-dependent perturbation theory. But
oh, you did. I see.
I guess the way we approached it was we had these like 2 equations. I guess it's only for a 2-level system, but you can have like an equation for the time derivative of each of the coefficients in your superposition. So how does that exactly relate to the method we're using here? Because I don't remember we went into the interaction picture. I think we derived these differential equations and used those.
I think what you did is Rabi's formula. Is that correct?
Yeah, I think that's it. Yeah.
Right. So in that case, it's a 2-state system, and simple enough that you can work it out exactly. You didn't have to rely on perturbation theory to work that out. Here, we are specifically looking at the perturbation theory. So the spirit of what we're doing is actually very different.
Okay, that makes sense.
And of course, when you apply the formalism we are using right now, and then try to implement it the 2-state system, and if you work out this time evolution operator, which you can actually work out exactly in that case, then it leads to the same answer. And then you can re-expand your exact result in power series and perturbation theory, and that would actually reduce back to this formula if you actually do it that way. So everything is consistent. right? Any other questions here? Good. So as we advertised, this is something we can now apply to for the decay of the 2s state to 1s state using this Hamiltonian. And as I said already, I use different parts of this interaction Hamiltonian differently. The last piece is used in this first order expression. And the first two terms are used in these the second order term to get both terms consistently. Namely that if you look at the power of the electric charge E, that's the expansion parameter, it turns out, then the second term has order E squared because I have E here, E there. So this first term comes out to be E squared. Also, using these first two terms twice, first two terms come with the power E, not E squared, but you use it twice. So this whole expression also is order E squared. So both of the terms are now coming at the same order in perturbation theory. That's why it is consistent to add them up and take a square of it. So that's how we actually view the perturbation theory in terms of the power series expansion in E. What to be more correct is a power series expansion in fine structure constant, which is dimensionless small number. Because fine structure constant 1/137 is small, it is a good expansion parameter in power series, which converges fairly well. Okay, so that's the idea of how to apply the perturbation theory to the process of 2s going to 1s. I hope this is very clear. Any questions about that?
Could you just repeat like the justification for why like we have these two terms being the same order in this case?
Yeah, so if you look at this interaction Hamiltonian here, which is just a point particle coupled to the vector potential, there is an overall factor of E, which multiplies these two first operators. So each of these Hamiltonian is order E. So this V I use for the second order, the perturbation is order E for this matrix element, order E for this matrix element. So the whole term is order E squared. On the other hand, for the first term, we use this last term in the Hamiltonian, which has E here and E there. So the Hamiltonian itself is order E squared, which is sticking over here. So this matrix element is order E squared. So it turns out that this first term is order E squared. The second term is also order E squared. So it makes sense to sum them up and take the square of the whole thing. Does that answer your question, Anna?
Yeah, thank you.
Okay, good. Any further questions here? Again, this is one of those things that, you know, in order to get to the physics result, you have to go through so many steps and you can get easily lost on the way. But I'm trying to, you know, break down every step as clear as possible. So hopefully you get the big picture on what's going on here. All right, so we finally apply this to this 2s decay. And in order to do so, I have to go from this initial state with this interaction Hamiltonian to the intermediate state with energy denominator and come back to the 1s state. And we know in order to get 1s state, this causes dipole transition. So this intermediate state M should have L equal 1 from the selection rule. And lowest energy state that will satisfy the selection rule will be 2p. So that this transition is from I, initial state 2s, using this dipole operator to go to 2p, and energy denominator 2p state, another dipole transition to go to 1s. You also sum up this 3p state as well. So 1s through the dipole transition going to 3p state, and 3p state, yet another dipole transition to 1s state. And intermediate state can also be 4p and all the other p states in the entire energy levels. So this sum over m is supposed to sum all of them up. So we are not going to actually do that full calculation here. Only thing we're going to do is look at the powers in fine structure constant, which I told you is the expansion parameter, and see how what kind of the number would come out of it. So that's what I'm doing over here. So 2p to 1s decay, which we discussed on Wednesday, we actually computed this process exactly. And we have this power of h over 2 epsilon of omega q coming from the normalization of the motor expansion of the vector potential. And omega q is the frequency of the photon emitted, which corresponds to the energy levels of the hydrogen atom. And I talked about the fact that energy level of the hydrogen atom is basically alpha squared times mc squared, which comes downstairs. So this prefactor is alpha to minus 2 power. Then comes the sum of the final states, which is the integral over the momentum of the photon, which comes together with the delta function. So the radial integral will be done using this delta function, because the magnitude of the momentum q times speed of light is the energy of the photon that satisfies the energy conservation law from delta function. So 1 power of q is gone, but I still have the q squared d omega for the solid angle integral. So there is a power of q squared. Each q is basically the energy of the photon. So this goes like alpha to the 4th. Finally, there is another factor we need to get from this matrix element squared. And matrix element is the matrix element of the dipole operator together with energy difference. Remember, we rewrote P over M using the commutator of X and H naught. H naught piece gives you this energy difference, and X is what remains in this matrix element. And just to count the powers of alpha, this matrix element is basically of the order of the Bohr radius. Bohr radius, it was like 1 over alpha. And so this is Bohr radius squared because you're taking the square of this matrix element. Energy difference is of the order of alpha squared. So that squares to alpha to the 4th. And there is yet another factor of alpha because there is an E in here. E squared over epsilon naught is alpha. And knowing that alpha A, the Bohr radius goes like 1 over alpha, that cancels 2 powers of alpha downstairs. So this ends up being alpha cubed. So end result is that alpha to minus 2 power, alpha to the 4th power, alpha to the 3rd power, and they add up to alpha to the 5th. And that's indeed the result we have gotten when we actually went through the calculation of the 2p state decaying to 1s state. So the decay rate of the 2p state goes like alpha 5th to mc squared. And indeed, that was the answer we have gotten. So the reason I went through this power counting in alpha is because we would like to contrast this power counting to the case of the 2s state decaying to 1s state. And we worked out even the number of this. So decay rate of the 2p state was basically a billion per second. And as a result, the lifetime of the 2p state was about 1 nanosecond. What happens when we go to this 2s state decay? We have now 2 powers of the vector potential. Here, you stick in 2 powers of vector potential right there. In the second order, you stick in 1 power of vector potential here, another power of vector potential here. Once again, you have 2 powers of vector potential to get 2 creation operators of the photons. So I get this prefactor twice, that's alpha to the minus 4th. Then you work out this matrix element. So it turns out that both terms have the same order in alpha. We argued about that on the previous slide. And if you stick in this, the momentum operator in here, going to the intermediate state M, so I change the notation to I to avoid the clash of notation with the mass of the electron. And another matrix element over here. And so that gives you this whole expression over here. And you can count the power to be alpha squared. Then you have now the phase space integral over 2 photons instead of 1 photon. So I have 3 powers of Q here, 3 powers of Q there. The overall energy conservation would remove 1 factor of Q, but I still have 5 powers of Q left. And each Q is the energy of the photon. So that goes like alpha squared. So you end up with 10 powers of alpha at the end of the day. And you put them together to find the decay rate to be 8 power of the fine structure constant. So now you can see that this decay rate is much more suppressed compared to the decay of 2p state by 3 powers of alpha. That's already something like 3 or 4 of the magnitude. And I'm not doing the calculation in full, but if you actually go ahead and do the full calculation, summing up all the intermediate states, then you find a decay rate that's of the order of 10 per second, as opposed to billion per second. So this is a big, big difference, right? So that is due to this factor of alpha cube that suppresses the decay rate of the 2s state to 1s state. So we say 2s state is metastable. So typical atomic transitions happen on nanosecond time scale, but this is extremely long-lived, which lives over the second and even more. So that's the decay rate of the 2s state. So that's something you can see just by looking at the powers of alpha. You can see why this is metastable, is very long-lived. And detailed calculation gives you a precise prediction on the decay rate of 2s state of the hydrogen decaying to 1s state by emitting 2 photons. Okay, let me pause here. Are there any questions about this?
I guess I just had a general question.
Okay,
so
go
the
ahead.
perturbation need not be time dependent in order to induce time dependent transitions. Is that correct?
So the matrix elements we are computing are no longer depending on time because we have done all these time integrals when we derive this formula, right? So we carried out all this time dependence already. So we did rely on the time dependence of the perturbative expansion, but because we have done the time integrals already, the expression we are using in the end on the amplitude don't seem to have any time dependencies left. Well, that's because we have already done the work. We are already relying on time-dependent perturbation theory and have done the work to reduce the expression to something that doesn't manifestly depend on time. So that's why we are using this result as a summary here, that it doesn't seem to depend on time at all, but secretly it depended on time, for example, the delta function reducing the time interval, and hence we are looking at the rate. Looking at the rate means you are looking at the probability per unit time. You never get that kind of expression if you hadn't thought about time dependence in the process. Does that make sense?
Yeah, okay.
Any further questions? Trying to get back to where we were. Okay, almost to the end. Okay, gotten there. So now that we have calculation, of course, we'd like to see if that agrees with the data. I actually could not find the data for this. And that's because this lifetime is so long, which means it's a very rare phenomenon. And if you have a gas of hydrogen, before this decay happens, hydrogen gas start to sort of hit each other, and the hydrogen may get excited to 2p and decay much more quickly that way. So this kind of process is extremely rare and difficult to measure. And apparently, at least I couldn't find the data on this one. But you can look at these ionized atoms, like a helium plus, and helium plus means you have only one electron circulate, going around the helium nucleus of charge 2. So the calculation is exactly the same thing as what we have done with the hydrogen atom, because it's a single electron system. And thanks to the fact that Z, the atomic number, is larger, it turns out that the decay rate is shorter the decay lifetime is shorter, decay rate is bigger, and that becomes not as rare process as what it is for the hydrogen atom, so that you can actually measure it. And this is the comparison of the theory calculation to the experiment. And if you go to bigger atoms, like oxygen 7+, oxygen, of course, has 8 units of charges of the atomic number. So normally, oxygen atom have 8 electrons. But if you ionize it 7 times, that's the meaning of 7+, you again have only 1 electron orbiting around the oxygen nucleus. So all of these ions have only 1 electron. So that's the same kind of calculation you would do for the 2s state of the hydrogen. And then you can make the prediction, and then you can do also the measurement. And you can see that in all cases, the agreement is actually very good. So second order perturbation theory does work. You can look at much more rare process compared to what you have done with the first order Fermi-Gaussian rule using second order perturbation theory. And then again, you see that there is a good agreement between what you do with the second order perturbation theory and what you measure in the experiments. So I hope this convinces you that second order perturbation theory is a good thing. Any questions about this? All right. So this is the first example where I apply the second order perturbation theory to some physical process. But there's yet another process which is very important, which is the scattering of the photon of an atom. So the idea is very simple. You have an atom sitting here. You send in a photon, and then this atom scatters the photon in an off direction. So that's the scattering process. And in the case of scattering process, you speak about a cross section. And you may not be familiar with this expression called cross section. It is a rate of transition per unit flux of the photon coming in. The idea is that the cross section has a unit of really cross section, namely length squared. And that's because the rate of the transition has the unit of inverse time, as we have been talking about. But the flux of the photon is how many photons you send in per unit area per unit time. So the flux of the photon has the unit of inverse squared length and inverse time. So that's the unit for the flux of the photons. So again, the flux of the photons is how many photons you send in per unit area per unit time. So that's the dimension of the flux. So if you compute rate of the transition per unit flux of the photons you send in, you divide T inverse by L to the square inverse and T inverse. Then T inverse cancels. And now how comes this unit of the length squared? And that's why we call this cross section. But intuitively, the idea of cross section makes sense. It's sort of like throwing darts on a target. And the probability of hitting the target would be proportional to the cross section of the target. The bigger the target is, easier to hit it. The smaller the target is, it's easy to miss. So the rate of scattering can be described by basically how big the target is. And that's why this has a dimension of the cross section. So whenever we talk about the scattering process, we speak about the cross section of the process, which is sort of like the size of the target. So the bigger cross section tells you how often you are supposed to hit the target, and therefore the rate of the process happening is larger. In the case of sending photon with the box normalization, then flux is described by C over L cubed. So 2 powers of L is really per unit area in the box normalization. But box normalization is periodic in space, right? So if we have a photon going through the box, over time interval of C over L, the photon comes back from one edge of the box to the other edge of the box because it's periodic. So the photon is there inside the box for every time interval of C over L. So that's why the flux of the photon in the box normalization of this periodic boundary condition is given by C over L cubed. Indeed has the right dimension to have L inverse squared and T inverse because of the factor of speed of light over here. And this is the flux we use in order to compute the cross section. And we again expect the end result, you compute the cross section, should be independent of the size of the box, and we will verify that. But anyway, what you do is to compute the rate of the process of the scattering using perturbation theory, and then divide it in the end by a factor of C over L cubed to predict the cross section. And we hope L dependence would cancel out when you actually complete the calculation. So what we do then is that compute the rate of the process. We already have the formula for that from the perturbation theory. First order determines golden rule again. Now we have the second order piece as well. And so this whole thing over here has the unit of rate. And then you divide this rate by the flux of the photons. So the inverse of the flux is L cubed over C over here. And this whole expression then has the unit of the cross section, which we call sigma. So whenever we talk about a scattering process, what we want to compute is this cross section, which has the unit of length squared. So that's what we would like to compute. Any questions about this? I'm actually curious. In the quantum mechanics class, did you see discussions on the scattering process in cross-section?
At least last semester's 137B, we covered scattering.
Okay, so you have seen this kind of expression before then, the sigma, which has the probability of the scattering process described by this cross-section that has dimension of length squared.
Yeah, if I recall. I mean, I don't remember all the formulas exactly.
Okay.
Yeah, I've definitely seen sigma before. So
okay, yeah. All right, so we go ahead and actually compute this for the scattering of the light of an atom. So in this case, the initial state is atomic state, let's say ground state, 1s state with a photon. That's the initial state. Final state is also, let's say, the ground state, 1s state of hydrogen and the photon, but in a different momentum of the photon. And the interaction you put in is again the same Hamiltonian we used before. And if you remember the form of the Hamiltonian, the last term had E squared A squared, right? And A squared has 2 powers of the vector potential. So I can pick one creation operator from it, 1 power of annihilation operator from it. So you can annihilate the initial state photon and create the final state photon. So that is the contribution from the first order perturbation theory. But I also need to use the second order perturbation theory, again, in the spirit of the same power in fine structure constant. And the perturbation theory from the first 2 terms in Hamiltonian has only 1 power of the vector potential. So I can use it in 2 different ways. One way is that I have initial state with 1 photon. And this perturbation would annihilate that photon so that intermediate state has no photon in it. And then you use another factor of the A, namely creation operator photon, to create a photon for the final state. So in this case, intermediate state has no photons. But another way of doing perturbation theory is that I have initial state with a photon. Perturbation would create the final state photon so that intermediate state has 2 photons in it. Intermediate state has, in this case, still the initial state photon, but also the final state photon. Then for the second time, I use the perturbation theory. So this V has the annihilation operator in it. So this V annihilates the initial state photon, which is still in the intermediate state. And that leaves only the final state photon in the final state. So there are two ways of going through this intermediate state. Intermediate state may have no photons, or intermediate state may have 2 photons. So there are now 3 kinds of contributions in this perturbation theory. So this first term would do annihilation of the initial state photon and creation of the final state photon all at once. But second order perturbation theory comes in 2 steps, and therefore intermediate state may be a state with no photons in it, or intermediate state may have both initial and final state photons in it. And hence there are 3 kinds of contributions to this whole amplitude of the process. Any questions about this? Let me stop here for a moment. It's okay? All right. So that's what we do here. And again, let us do just a power counting. But in this case, we can do power counting in alpha 2, but we are very much interested in how the end result depends on the energy of the photon. And energy of the photon, according to Dubroit's relationship, is basically h bar times omega. So what we are interested in is dependencies on omega of the angular frequency of the photon. So we are looking at the pieces which look at the second power in the vector potentials. So in all of these terms, they have the 2 powers of vector potentials, 1 annihilation operator for the initial state photon, 1 creation operator for the final state photon. And each of the initial state photon annihilation operator and the final state creation operator comes with this prefactor, which has 1 over omega in it. So when you separate out a creation operator and an annihilation operator from the vector potential, I get 2 powers, inverse powers of the angular frequency for the photon. And then we need to sum over the final state together with a delta function. So using this delta function over the sum of the final state photon sum is the phase space integral. But the radial integral is done using delta function, so that's gone. So I'm left with second power of the Q integral left, together with a solid angle integral for the final state photon direction. And Q times C is the energy of the photon, so you get 2 powers of omega from there. And we are interested in the limit where energy of the photon is very much smaller compared to the atomic excitation energies. And so that's the limit we are interested in what is called the Rayleigh scattering. So Rayleigh scattering is basically the limit where energy of the photon is small compared to the atomic transition energies. And this would greatly simplify the calculation. For example, the energy denominator here is very big compared to the energy of the photon. So that you can do approximate expansion in the energy of the photons. It turns out, though, that in this sum over 3 contributions, directly transition to the final state, transition going through the intermediate state with no photons, and transition going through intermediate with 2 photons, there is actually a fairly delicate cancellation among them. So it turns out that this middle thing, the transition amplitude, turns out to be suppressed by the energy of the photon by the second power. This is suppression because this energy of the photon is smaller compared to typical transition energies. And the showing this cancellation is done in the lecture note, photon.pdf, and you are encouraged to look at this, but it's fairly technical. It takes a couple of pages on a LaTeX file to actually go through this calculation. So it's fairly non-trivial, and I don't want to show that on slides because it's technical and long. I'm just telling you that this cancellation does happen, and matrix element is of the order of omega squared. So if we actually put they together then matrix element can be re-expressed in the following fashion. after noting this cancellation so that I factor these 2 powers of omega squared out to get omega to the 4th power. And if you put everything together, in the end, I find the expression of the cross-section, which goes like this. So the 2 powers downstairs of omega, 2 powers of omega upstairs, of course, cancels. Matrix element is omega squared, which gets further squared in the cross-section. That's why you have omega to the 4th power as a dependence of the cross-section on the angular frequency. And I realized that what the absolute squared is outside the windows. Let me put that in here. Okay, I fixed it. Okay, now it fit inside the window. So this whole thing in the amplitude is order omega squared, which I factored out because of the square thing, so that this is actually omega to the 4th power. And everything else now depends on basically typical size of the position operator, which gives you the Bohr radius. At least that's the order of magnitude. You have the energy of the photon downstairs. I'm sorry, the energy of the atomic excitation energy downstairs. And you can typically ignore energy of the photon relative to atomic excitation energies. So what is downstairs is the atomic excitation energies. Then you can do the power counting over alpha. So this is order alpha squared, 1 over alpha, 1 over alpha. You have alpha squared up front, and you can go through the counting of alpha. So then in the end, you can sum it up into this following expression at the end of the day. So 1 over omega to the 4th. Omega is the frequency of the photon, and together with the speed of light, that's the c over wavelength of the photon. So omega is c over lambda. So that's how you end up with 4 powers of the wavelength downstairs. And you can do a dimensional analysis to get the correct unit for the cross-section, because the wavelength has a dimension of unit, of length, obviously, with the wavelength. Then you have to put 6 power of something has a dimension of the length. The only candidate is the Bohr radius. So cross-section turns out to be Bohr radius to the 6th power over wavelength to the 4th power at the end of the day. So at the end of the day, you don't need to go through this full calculation if you had known that there is this non-trivial cancellation of matrix element, so that this thing here is of the order of 1 over wavelength squared. And when you square it, you get 1 over wavelength to the 4th power. And the rest can be determined just by the dimensional analysis using Bohr radius. But of course, without doing the calculation, we wouldn't have known that there's this cancellation, so that it depends on the 2nd power of the angular frequency. So an end result looks like this. So this is the expression for the Rayleigh scattering cross-section. And the main point here is that the cross-section is small for longer wavelength by a 4th power. 4th power is a big power. So if you have the cross-section, then you can multiply it with the density of the atoms in the atmosphere. So here I'm simply using the case of the standard pressure and temperature and pressure. As you know, the SDP refers to 300 Kelvin and 1 atmospheric pressure. And you know this number from chemistry class. 1 mole of atoms under the standard temperature and pressure is 22.4 liters. And by multiplying the density and the cross-section, you get something of the unit of 1 over length, because the number density has the unit of the inverse volume. So length to minus 3 power. Cross-section has length to 2 power. So density times cross-section has a unit of 1 over length. And inverse of that gives you the mean free path. So that makes sense. If the cross-section is larger, then photon would hit the target right away, so mean free path is short. If the density is higher, again, you have more targets, So photon would hit the target quickly and mean free path is short. So n sigma inverse is what gives you the mean free path of the photon in the atmosphere. Then you can just plug in these numbers. We know the Bohr radius. And for a photon, for the blue light, that's about 4,000 angstrom or 400 nanometers. And you plug in these numbers with the density of the atoms in the atmosphere given by the standard temperature and pressure. And you can work out the mean free path of the photon, which is long, about 1 million kilometers. And this is a good thing, right? So mean free path of the photon is way longer compared to the thickness of the atmosphere, which is at most something like 100 kilometers at best. So there is basically no even single scattering of the photon through the atmosphere, so that the scattering is a rare thing. That's why you can see the sun. If this mean free path is shorter compared to the thickness of the atmosphere, then all the sunlight gets scattered in the atmosphere, so you don't see the sun directly. You lose the straight path to the sun, so then you wouldn't see the sun. The fact that we see the sun at all is already a confirmation of the fact that the mean free path of the photon is longer than the thickness of the atmosphere. So that's good. But now we have the steep power, which is the fourth power in wavelength. If you stick in the red light instead, which may be, say, 7,000 angstrom in wavelength, then the mean free path is 10 times longer for the red light because the wavelength is longer that suppresses the cross-section. So the blue light has 10 times shorter mean free path compared to the red light. In other words, blue light has 10 times higher probability of getting scattered by atoms in the atmosphere. And this behavior actually makes sense, which goes back to this cancellation in the matrix element. Photon couples to electrical charges. So you see the interaction Hamiltonian that goes P minus EA. So A couples with E, namely electrical charges. But atoms are electrically neutral. So photon doesn't notice there is an atom because it doesn't have an electrical charge. But when you dig in and start looking into the structure of the atom, the photon may notice that, okay, there is actually charge in there. There's a cancellation between the charge of the nucleus, charge of the electron, but there is actually electrical charge objects in there. But long wavelength light doesn't see finite structure, therefore doesn't notice that there is an electric charge in here. But the shorter wavelength light would resolve the inner structure of the atom and notice that there is an electric charge inside and can get scattered by it. So it makes sense that the shorter wavelength light would see more structure, inner structure of the atom, and notice that there is an electric charge in there to get scattered by it. So this dependence that long wavelength light gets less scattered by the atom, short wavelength light get more scattered by the atom, makes sense. I hope that makes sense to you too. So main result is that because the long wavelength light doesn't resolve the inner structure of the atom, it doesn't get scattered by neutral atoms. But as you go to shorter wavelength, the scattering would increase in probability with a steep power of 4. So there isn't even an order of magnitude difference of how often the light gets scattered between red and blue. Let me stop here. I'm sure there are questions about this.
I actually have a like a request. Is it possible to introduce Raman scattering briefly? Because you just talked about the Rayleigh scattering, and there's should be another or I mean, famous region that can you understand my question?
No, I did not. Can you repeat that
Oh,
for me?
sorry. Yeah. I mean, is it possible to introduce the Raman scattering like briefly? Because you just talked about Rayleigh scattering.
Oh, Raman scattering.
Yeah.
Okay. So Raman scattering is for the photon with much higher energies. And so I didn't prepare a slide here. It will come back later on for a particular case of resonance scattering, but I was not planning on discussing Raman scattering in general. Maybe I can expand the lecture notes to have some brief discussions about it. Is that okay?
Okay, yeah.
Yeah, I don't have slides prepared for that. So that's the only thing I can do. All right, any other questions?
Yeah, this might have been explained a while ago, but could you explain how we get the normalization factor of the vector potential, the first term of the second line?
Okay, so that goes back to the previous lecture, and let me see. Stop share. This is from Wednesday, and this is the expansion of the vector potential in creation and annihilation operators. So the idea was to quantize the vector potential as a field, which is basically like X in harmonic oscillator. So that can be expanded in terms of sum of annihilation and creation operator. And in order to satisfy the Coulomb gauge condition, we had this polarization vector. And the rest is fixed by the canonical quantization condition of the vector potential that A and A dot commutator is 1 over epsilon naught. So that was the canonical commutation relation. So all the factors get fixed by that normalization requirement. And as a result, we have gotten this prefactor h bar over 2 epsilon naught L cube omega p. So this is the factor that kept appearing in power counting discussions in powers in alpha, or powers in L, or powers in angular frequency. So this is the prefactor that appeared in the mode expansion of vector potential. Is that the question you're asking?
Yeah, thanks. Sorry to make you go back so far.
Oh, no, fine. That's fine. Because, all the processes are pretty lengthy. So it's very easy to lose sight on where you are in the long process. And so this is always very good thing to go back to where you started out to make sure that everything sort of makes sense and you get a big picture. So I appreciate that kind of question. Any other questions?
So I guess observation we made for, the scattering going to 0 as lambda increases infinity, we didn't, when we derived the equation, we didn't actually consider the inner electric charge, right? It just
we did, right? So this is the interaction Hamiltonian we use for the electron. And we use the states in the hydrogen atom. So this calculation already knows that we are looking at the neutral atom of electron bound to a proton. And that's the whole system is neutral. Am I answering your question?
I see. So I guess where do we get that it's neutral? So we have the electron position and charge, but where do we get the corresponding charge?
Because you are using the wave functions of electron in the Coulomb potential.
Oh, I see. Okay.
Thank you for asking that question too. Any other questions here? Okay. And I believe many of you already know that this behavior, that the Rayleigh scattering cross-section is suppressed at long wavelength, is and enhanced at short wavelength, is the reason why the sky is blue. Namely that when you have when you're standing on the earth and looking at the sky, then you're looking at the sunlight, and sunlight, of course, can directly come into your eyes, which you shouldn't do because that would burn your retina. But we have learned that the thickness of the atmosphere is much thinner compared to the mean free path of the photon. So that's why you do see the direct sunlight, which you shouldn't. But at the same time, the sunlight would hit atoms in the atmosphere, and the blue light gets preferentially scattered by the atom in the atmosphere. So if you look at off direction, not into the sun, but off direction into the sky, all you see is this scattered light coming into your eyes. So the sunlight contains this entire spectrum from red to blue, and red portion doesn't get scattered very much. The blue portion gets scattered a little more by 10 times, as we have computed on the previous slide. So the light that comes from the atmosphere, scattered light, is preferentially blue light instead of the red light, and that's why you see the sky being blue. On the other hand, at the time of the sunset, the light travels through the atmosphere for a long distance because it comes from the side instead of directly on top of you. So while the light is traveling through the atmosphere, the blue portion of the light gets scattered away, so you start to lose it. What remains is mostly the red portion of the spectrum of the light, and that's why you see the sun to look red at the time of the sunset. So that's why the sky is blue and sunset orange, and that's because of this Rayleigh scattering, which preferentially scatters light for the shorter wavelength and hence the blue light. So I'm sure you know this story, but any questions about this?
I just had a question actually about
Okay, go ahead.
Previous like calculations of the cross section. I was wondering, so is that solid angle integral, like are we integrating over the, I mean, I know we have this sum over all the possible like photon modes, but are we also summing over all the possible like atomic states? Or
no. So here I'm specifically choosing the initial atomic state to be the ground state and final atomic state to be also the ground state.
Okay, okay.
And in principle, you can have the excitation of atomic state from the ground state to an excited state if the energy of the photon is high enough to cause that excitation. But here we are looking at the limit where energy of the photon is much, much smaller compared to the atomic excitation energy. So in the case of hydrogen atom, the excitation from 1s to 2s is already in ultraviolet. So that's high energy photon compared to red and the blue light we are talking about over here. So we are in this limit, and therefore you cannot excite the atomic state by conserving energy. So here we're only specifically looking at the ground state going to ground state. You still sum over all possible final states, but the sum over the final states is the ground state of the atom and photon going into arbitrary direction. So the sum turns out to be only the integral over the solid angle for the final state photon in the end.
Okay, okay.
Okay?
Yeah.
Thanks. Any further questions on this? Okay. So when I talked about this in some quantum mechanics class in the past, one of the students asked a very good question. So if the short wavelength light gets scattered more, why is the sky blue instead of violet? Because the violet has even shorter wavelength than blue, so it gets indeed scattered more by the atoms in the atmosphere than blue. And I believe the reason is this. So this is how well our retina, visual pigments, would absorb light. And blue is somewhere around here, and violet is down there. So basically that quantum efficiency of our eyes to detect violet light is far less than how we detect the blue light. And of course, we have 3 filters or 3 different visual pigments on our retina. That's why we detect color with RGB. So you have the red, blue, red, green, and blue. And this blue visual pigment would absorb blue light and basically convert the energy of the photon into the motion of the electron in the retina that transmits the electrical signal through the nerve to the brain. And that's how we think we have seen the light, right? But the probability of the violet light getting absorbed by the visual pigment in our retina is lower than blue. So if you fold in this efficiency with the spectrum of the light coming from the sun, which does have plenty of ultraviolet light indeed, and here is the blue, this is UV, and this is the violet. There's a big portion of violet in there, but the probability of absorbing the violet light by our human retina is so small. So in the end, it gets dominated by the blue color in our perception. So that's my understanding of why the sky is blue. So in addition to this behavior of the Rayleigh scattering, which goes like 1 over wavelength to the 4th power, so that the scattered light is dominated by actually a violet more than blue. But we don't see violet light very well because of low efficiency. So that's why sky is blue. And so that's the way I explain why the sky is blue. So there's one little additional step to know why the sky is blue instead of violet. Any questions about this? Okay, so that ends the story about why the sunset is orange and the sky the blue. And this is a picture I took when I was just doing a bike ride up on the Grizzly Hills, Grizzly Peak, and there's the Golden Gate Bridge and a beautiful sunset. You know, we're really lucky that we live in this area to be able to observe this beautiful sunset. And anyway, so that's how we understand this picture. Sky is blue because sun is over there, it's in an off direction, and then the atmosphere scatters light, preferential blue that comes into our eyes. But if you look directly at the sun, then blue portion of the light got scattered away. So the remainder of the light is richer in red, and that's why the sky and sunset looks orange and red. And so this is really a great triumph that we understand something based on the quantum mechanical atomic physics calculation, why the sky is blue. Okay, so this is a good place to stop. There's still 3 minutes remaining, but I think I'm gonna finish here. And the next week, we will talk just briefly about the higher energy photon scattered by the light that can cause the excitation of the atomic state, which leads to a phenomenon called the resonance. And I will very briefly talk about this, and then move into the actual relativistic quantum field theory next. Now that we quantize the photon, we know the Maxwell theory is Lorentz invariant, but we still used non-relativistic matter particle for the discussion of these atomic states. But of course, we have to also make the matter part of the discussion relativistic as well. So we move into discussion of relativistic quantum field theory for matter particles, starting with spin 0 particle called the Klein-Gordon field, and then move into spin 1/2 particle called the Dirac field next. So that's the plan for the rest of the class. Okay, any questions? And based on popular demand, I did postpone the deadline for the current homework problem till the next Friday, but I will post the next homework problem also today. So hopefully you can manage that. And I try to make it light. I actually haven't written the problem set yet. So I try to make it a little bit light than usual so that I hope you can actually deal with the 2 homework problem sets by the next Friday. Okay, then see you next week and have a good weekend.
Thank you.
Thanks.
Thank you.
Bye.
Thanks.